All right. Hi, everybody. Everybody ready? Okay, I got some questions about homeworks and stuff. I don't know if it's from anyone in this class, but I'll get to those this afternoon or early morning. I've got a little bit of time that I can deal with stuff like that. I think that's about it. So we finished up on Friday with doing a chi-square test. Let me just double check. I think that was for a just a simple dihybrid cross. What was the day on Friday? That was the 5th. Right, yeah, that was a simple dihybrid cross. Okay, so what I want to do today, well, not dihybrid, mono. You're right, Jenny. Thank you. I don't know why I keep crossing those two up. So what I want to do today is to work through with all of you a more complicated. It's Monday. Thanks, JM. Yeah. It's always worth reminding me what day of the week it is. Yeah, so we're going to do a more complicated chi-square cross, right? So what I'm going to do is I'm going to just kind of make up some data, essentially. And I want to go through in steps with you, right? So let me just make sure I've got logged into Blackboard so I can bring up that table quickly. Actually, while that's logging in, we can get on with this. Okay, so let's see, what can we do? What I want to do is I want to do I'm going to type this all in the chat box so we have a record of this, and we can also kind of go back to the data as well. All right, so we have oops, if I can spell. What are we going to do? Let's do black, long hair, cat. I used dwarfs with the other class, which just got a little bit convoluted, right? So I'm just going to stick with something simple. Crossed with a double recessive. What would be? It would be ginger. All right, so that's the P generation, right? Okay, so quick questions to the class as always. What's the phenotype of, or phenotypes, because there are two, of the F1 generation? Shout it out or type it in, whichever you prefer. Come on, peeps. It's a dihybrid cross. Just gave you the P generation. What's the F1 generation? Yeah, exactly, right? And we know it has to be because we know that the parents are true breeding, right? They're homozygous, either dominant or recessive, right? So what's the only genotype you can get in the F1 generation? Kind of tied with Jananie's answer. What's the only genotype you can get in the F1s for this cross? Yeah, double heterozygous, right? Because remember, we're dealing with two different genes. One which encodes the trait of fur color, and the other one which is the trait of fur length, right? Okay, so that's just, I just want to give you some recap, kind of keep, going over that stuff because it's important to know. Okay, let's make up some data. So we have the parental dominant, which is going to be the black long hair. We're going to have 965. Now I'm going to give these in the kind of classic order, right? So next is a non-parental combination, which will be, let's say, ginger long hair. We're going to have 125. And we're going to have black short hair. Again, this is another non-parental, right? Essentially, you don't see this in the parents, right? That's what that means. We're going to have 164. And then we have our last parental, which is going to be our ginger short hair. Just making sure this is all congruent. And that is going to be about, I don't know. There you go. All right. So these are the data for the F2 generation. I should have written that. Let's put that down. I can't even spell that right. Okay. So we have our data. What's the very first thing that we have to do when we're doing a chi-squared test? Sorry. All right, we've got to work out the total of our observed data, right? So add all those together and let's see what we get. All right, so hopefully everyone is here because they want to do this stuff. Awesome. Good job, everybody. No decimal point there. You can use a comma if you want, Raylene, but otherwise that would read as 1.444, which would be a very weird cat. All right, awesome. So, okay, what's next, right? So now we have the total number of observed. What do you need to do next? What are the numbers that we need to calculate, right? We need the ratio, right? So we need our expected, right? Exactly, Sophia. And so we're going to calculate our expected values using the ratio of phenotypes that we expect, right? And so given that this is a, pardon me, it's my granola coming back up, say hello. Given that we know that this is a dihybrid cross, what's the ratio of phenotypes we'd expect in the F2 generation? Dang, you fast. All right. Okay, so how would you turn that into a fraction or something that you'd be able to calculate your expected with? Now, that's good. All right, so what kind of fraction are we looking for, let's say, the dominant parental? What fraction of the total would we expect if our ratio is 9 to 3 to 3 to 1? Yeah, exactly. Okay, so this is kind of the next step of working out the expected. First is to add all of your observed data together so you get the total. Then you need to figure out, well, of that total, how many do I expect will be whatever, right? And so that's the second part. So now you need to work out for all of these different phenotype combinations above, right? Black long hair, ginger long hair, black short hair, and ginger short hair. You need to work out using that total the expected numbers based on the ratio that generally typed in, right? So you need to times the total, which is 1,444 by 9/16, or what is that? That's 0.5625, I think. Yeah, that would work, Rogelio. Yeah, or 1,444 times 9 divided by 16 is another way of doing it. You know, I don't think it matters which way around. Yeah, so work out that. What's that number that you get? All right, okay, good. And so Sophia typed in with 2 decimal places, which is excellent, right? One thing that you want to remember is not to get rid of those those numbers after the decimal place, right? So don't round up or round down. Even though obviously you can't have quarter of a cat, that would be odd. You still use those because those are kind of your theoretical expected numbers. Okay, so I want you all to do that for the other three phenotype combinations too. And give me a little bit of time to do that. While you do that, I'm going to make sure Blackboard is doing what I want it to do. All right, good stuff. So the fun thing, Rogelio, is you only need to do that calculation once, right? Because you have two that are 3/16 of 1,444, right? Your two non-parental phenotype combinations. So all you need to do now is work out what is 1/16 of 1,444. All right, awesome. So we have our expected values now, which are 812.25, two lots, right, of 270.75, because we have two expecteds that are 3/16 of the total, right, our 233s. And we have our final one, which is our double recessive parent, or parental rather, and that's 90.25. Okay, so for all four of these combinations, you need to work out actually, I keep telling you stuff, right? You need to tell me stuff. What's the calculation that you need to work out for each of these? Yes, that. But don't forget, this is the sum of, right? So you need to work out the observed minus expected squared divided by the expected for each one of these phenotype combinations. Right, so for example, I'll give you the first one. It would be the observed is, I've got to go all the way back up here now. Crab sticks. This is the downside. All right. It can be 965 minus, it seemed like a good idea at the time. There you go. 812.25, I think it was, squared divided by 812.25. Let's just double check, make sure I've got the right numbers. Yeah, that's right. So that's the first one, for example. Your observed is 965, your expected is 812.25, right? So you calculate that. That is your chi-square for the dominant parental, right? Just for that one, right? We have three more that we need to calculate. So calculate that and then do the other three as well. And so we want to get the whole chi-square value, the sum of all of those calculations. Okay, so I'm going to leave you to do that. Obviously, I'm still going to be here, but I'm going to give you some time to work through that. All right, cool beans, Jan. So that's the first one, right? What are the second, third, and fourth? I think my cat alarm is going off. Dang, that's a lot of decimal places generally. So that's the second one. Okay, third and the fourth. And I hope that everybody's able to do this. If you don't, and really, you know, there are always going to be some people that get this a little bit quicker than others, not necessarily because they're smarter, but just because it clicks a little bit better, right? So if there are any of you that are kind of just sitting there going, what the hell's he doing? Or what's all these numbers coming up? Please ask, right? Please just go, hang on, I just missed the bit where you're doing whatever, right? Or I just don't quite get X, Y, and Z. That's totally great because I don't want you to be kind of left behind in the wash, right? This is stuff that you need to know to be successful in the exam, right? And so if there are any questions, even if we have the answers kind of going up here, ask, right? This is the downside of doing this stuff online. I can't see you. I can't see whether you're, you know, kind of shaking your head or like crying in a corner or something. Just pipe up and let me know. Okay, does everybody kind of get that, get what we're doing, essentially? Oh, that's totally fine. Just what my worry is that, you know, 5 or 6 of you might be like getting it, and then everybody else is like, whatever is going on, and that would be sad. I wouldn't want that to happen. Okay, good. And that's also part of the reason for kind of going over this again more slowly, kind of building time for you to do that. I'll be doing the same with linkage as well because that's more math basically. Okay, so what we need to do is this chi-squared is a sum of those values, right? So we need to add those together, right? So what is the total of all those 4 chi-square values? We need the total chi-square. That looks pretty good to me. Does everybody else get the same? Oh, not quite. All right, where's the discrepancy coming from? No worries. Could be Jelly who got it wrong. It never actually hurts to double check these calculations. Unless you're super confident that it's going right. I've got fat fingers and I sometimes type wrong. Okay, awesome. Cool. See, that's worth doing, right? Just to double check. Okay, so this is our chi-square value, right? So our chi-square, oops, get the caps lock off, equals 259.52. Hello, we just had a transmission. Is this alien life form getting some Morse? Oh, that's not as interesting. I think someone just has their mic unmuted. So right, so okay, that's our one piece of information. What's our second piece of information? Right, remember we need 3 bits of information for a full chi-square result. Now that's the third one. Good job, but we haven't got there yet. We need the second one first. What else do we need to know to calculate? There we go. Degrees of freedom. Awesome. Oh, good job, Jimena. Right, so how do we calculate the degrees of freedom? What's the little formula that we use? Yeah, right. So df equals n minus 1. Right, and so our n in this case is how many of those chi-squares did you add together, right? How many different conditions we have, which is 4. So our degrees of freedom is 3. Awesome. Okay, so now we have the 2 bits of information that we need to calculate our p-value, right? And again, our p-value is the probability of getting this result by random chance, right? And so in terms of chi-squared, really what we're saying here is that if we get a difference from our expected, that difference is occurring just by random chance. It's not because our expected values or our theory is wrong. Does that make sense? Yeah, so really what our chi-square is telling us is how good do our data fit our expected? And they're not going to fit perfectly because biology is noisy, but our p-values tell us if they fit well enough to be expected that any difference is just by chance, right? Okay, so what we need now is, let me just share my screen with you. Doopy-doopy-doo. You don't need to see my email. I'll have email from my wife telling me what to do with my kids. So, because she's away, we're not separated. She's away in Georgia right now for 3 weeks. Not that you really need to know that, but anyway. Okay, so this is our chi-square value table. You can also use this funky as chart thing down here, which if you give me a little while, I could figure it out. But it's not something that I find super intuitive. I just like using this. It's kind of like I guess, a working man's chi-squared p-value calculator rather than a thinking man's one, right? Which is what this is. So we've got our degrees of freedom here. We've got degrees of freedom 3. And so what we're looking for is whether or not our value is larger than or smaller than this value, right? If it's smaller than this value, right, so it's going to be over here, basically that's saying that the difference that we're seeing is simply occurring by random chance. I've got something come up in the chat. Not so much how likely, right? So the p-value isn't a predictive value, right? That's it's really based on what happened already, right? So it's based on what you observe. So it's not that how close we predict the observed will be to the expected, or vice versa. It's more how well do our observed fit our expected, right? So once you do the experiment, right, you start the experiment and you go, okay, I think this is going to happen, right? Once you do the experiment and you actually get your data for that experiment, how well do those data fit what you thought would happen? Now, obviously, they're not going to fit perfectly, right? Even if you look at Mendel's data, he never got an exact 3-to-1 ratio, for example, in a monohybrid cross, right? He always got something a little bit different. But you're always going to get something a little bit different. The question is that difference important? And what you're hoping is that no, it's not going to be important, because if it's important, that means that I've done something wrong. You know, my theory about what should happen is incorrect, because what happened doesn't look like it. Does that make sense? So you want the smallest differences as is biologically possible between what you expect and what you observe, right? Yeah. And so obviously if you have a really huge difference, right, that's basically saying that for most of your expected values, your observed data are largely different, right? Because remember, it's that difference between the observed squared divided by the difference between the observed and expected squared divided by the expected, right? So the bigger the number, that basically means the bigger the difference between the observed and the expected, right? And the only way you can get that big difference is if your expected is wrong, right? So really what the chi-squared is telling you is that, yes, your data fit well what you expect, and any difference is just random chance, or no, your data do not fit very well to your expected. Therefore, your expected is wrong or are wrong, right? Because there's obviously more than one. Right, so it's the kind of the familiar term of goodness of fit test is actually far more useful, right, than the chi-squared test name, because I mean, I don't even know what chi-square means. Something chi, I think, is difference, maybe. But either way, goodness of fit test is a much better name. And so if our data fit good, then we'd expect a difference smaller than this, right? A chi-squared value smaller than this. Okay, so given our degrees of freedom of 3 and what is our chi-squared value? God, chat is not very easy to navigate through. All right. Where is our chi-square value in relation to this? Is it a larger or smaller number? Think about that generally. We have, oh, okay. All right. So just stop for just a second there. Kind of jumping ahead a little bit. Right. First, we want to figure out if our chi-square number, right? This was 250 something or other. I can't remember exactly. Is that larger or smaller than this number? Oh, sorry, generally, Jimeno, I meant. So 250 is obviously much, much, much larger than this number, right? In fact, it's so much larger, it's even larger than this number here, right? So our p-value, not the chi-squared value, the p-value that we work out from that is smaller than p-value of 0.001, right? So we would type that as p-value, p is smaller than 1. And I'll just get to that in a second, but now we can write out, yeah, right. So this is really important because this is where things can get confusing. Let me just finish writing this out first. So the chi-square, I think it was 259. I'm just going to round it up so I'll save some time looking it up. Degrees of freedom, 3, p-value of 0.001. All right, so what this is actually really telling us is that we have a probability of 1 in 1,000 that the difference that we saw is purely due to chance. Right? Flip it around the other way, we have a 999 in 1,000 chance that something is going on that we're not taking into account. Right. If you think of it that way, right, this is a really, really, really small number, and it's really weird to have small numbers meaning more. But if you work it out as essentially this is a probability of something occurring by chance, if you flip it on its head and go, well, what's the probability that we got that result not by chance, right? Because we did something wrong or because something happened, then essentially this is a much, much larger number, right? It's a 9. So this would be 1 in 100 chance, right? P-value 0.01. 0.05 would be 1 in 20. So essentially you're saying it's going to be 1 in 20 chance it's not, hang on, tying myself in knots here. So 1 in 1,000 chance it's not happening, is happening by chance. 1 in 100 there's probability that it's happening by chance. 1 in 20 probability that your difference, your data you observe is happening by chance. So the flip side of that is that, you know, what's that, 19 out of 20 times you're expecting this would happen by chance, right? That's probably not helping. Let's kind of move on. I always get myself tied in knots when I talk about this stuff, right? So essentially, the smaller number, the more important, because that's the lower the probability that you're seeing this difference just by chance. Okay, so if we go back to the data, right? So sorry if I'm kind of confusing the issue a little bit here. It's a lot easier to talk about at this end than it is in the middle. This 0.05 is really just a line in the sand, right? This is the level at which we think that the difference you see is meaningful. It's not just random. And as that number gets smaller, it becomes more meaningful and less random, right? And so really this isn't a yes, no kind of deal. This is a past this level of probability, things become more meaningful. Above this level, they are less so, right? I mean, essentially, even if you're just above that, it's because it's a line in the sand, it's called not significant. Even though it looks like there is something going on, it just doesn't cross over that threshold, right? But once you get below that threshold, then the smaller the p-value, the more important the difference that you're seeing, right? Whether that's in a chi-square test or other kinds of test. So you're observed. They're about, oh, what is it about? So you're expected, oops, right. And so you can see now when we put it in this kind of format, it's like, okay, we're seeing about what we'd expect for the parentals, give or take, but there are far, far fewer non-parental phenotype combinations, right? Those ones in the middle. And this was pretty deliberate because essentially, if you see that in an F2 generation of a dihybrid cross, that's telling you that one of your assumptions about that dihybrid cross are wrong. And so what's the kind of the key assumption about a dihybrid cross, right? It's actually leads to one of the laws of one of Mendel's laws, the law of something. What's the key one for dihybrid cross where we have two different genes? What's our key assumption? This is taking you back a little while. That's good, but that's for a monohybrid cross. So that's talking about different alleles of one gene. It still applies to dihybrid cross because it applies to however many you have, but it's really in relation specifically to monohybrid cross. Yeah, Sophia, good job. So this is the law of independent assortment. And so that tells you that those genes should assort independently of each other, right? And you should get that 9 to 3 to 3 to 1 ratio. So the fact that you didn't, because up here you can see up in the chat a little bit, you can see that the ratio is off for the non-parental combinations. That tells you that your law of independent assortment is not applying, right? So one of your key assumptions about dihybrid cross that you did to generate those data is wrong, right? And typically that means that those two genes are linked, right? They're close enough on the same chromosome that they do not assort independently. And we'll get back to that much later, well, not much later, but in the next section of the course, we'll talk about linkage in depth. And this is kind of one of the ways in which you can test for that, and which we will be testing for that. Okay. Does that make sense, everybody? Kind of a lot to take in for one class, but we've got some lighter lifting to finish up with. Okay, good. So again, with things like this, they're just not just facts to remember, but they're actually kind of skills to learn in a sense, right? Practice makes perfect, right? So the more that you can do examples like this, and you can just make up your own, right? It's all I do. I don't have any kind of numbers prepared. I don't know what the answer is going to be, right? But you can just practice, right? Do a few of these. Then when you come to your exam and you have questions that tell you to do a dihybrid cross for one, a chi-square based on those data, things like that, this will be a very straightforward question for you to answer. And the good things about these kind of questions is that, if you can do a chi-square test, sorry, and you know what dihybrid cross is, you can't really get it wrong, right? You just have to follow those steps that we outlined today and you'll get it right. Right. So in a way, it's actually a more surefire kind of thing to figure out than, remembering the different phases of mitosis, for example, right? Because it's very straightforward, but you do have to know how to do it. Okay, so what we're going to do is we're going to just finish up with a wee bit of probability and probabilities. Okay, so the last two things that we're going to do is we need to cover independent, mutually exclusive events. Okay, so let's kind of get back up here. Make sure this is out of the way so I can see what I'm doing. Okay, so essentially, if you have events which are independent, right? So these are things where the outcome of the first event does not affect the outcome of the second or the third or the fourth or so on, right? They are independent. And so a classic one to think of is sex of your children, right? The first one, you have 1 in 2 chance of it being male or half probability of either sex. Second one, you have the same half probability because the sex of your first child has nothing, at least one hopes not, to do with the sex of your second child, right? Unless there's some kind of funky kind of familial thing going on where you tend to have all boys or all girls, which is a real thing, but it's you tend to only see that over generations rather than individual families. So if you have a boy for your first child, then you have the same probability of having a boy for your second child, right? Because they're independent. Another way of thinking about it is about phenotypes, right? So for different genes, different phenotypes, those are independent events essentially. Although, well, let's use P's again, right? Because we've already used this example, right? So the probability of getting around P, right, has nothing to do with the probability of getting a wrinkled P, getting a green P, right? Because those phenotypes are independent, right? So whether or not you get a round or a wrinkled P has nothing to do whether that P is green or yellow, right? They're independent. Does that make sense? So essentially, if you say, well, what's the probability of getting 2 of these independent events? You have to times them together, right? Because if you're, pardon me, I always use the example of playing poker. I don't play poker because I don't gamble and I'm really bad at it. But if you think about, well, what's the chance of getting a straight flush, right? I've watched enough TV to know like the different names of these things. Right, what's the probability of getting straight flush? Once in one hand. Well, I don't know what that is. Small, right? Okay, well, if you play a game of poker with some buddies, what's the probability of you getting 2 straight flushes in successive hands? It's obviously going to be less, right? Because those two hands don't have anything to do with each other, right? And so the likelihood that you're going to get two of these rare events happening is going to be far less than the likelihood of getting one of them. So you times those probabilities together, right? So in the example of having kids, probability of having two boys, right, is going to be the probability of having one times the probability of having another, right? So that'd be half times a half is a quarter. What's the probability of having three boys then? Questions to the class. What's the probability if you know anybody that has three kids, maybe three boys or three girls, what's the probability of having three children all the same sex? Yeah, exactly. You just continue the process, right? So instead of it being a half times a half, now it's a half times a half times a half, right? Which is an eighth or 0.125 as generally put. Okay, so essentially, the more times you do this, the smaller the probability that you'll get a certain combination of events, right? And so if you do it for 4 children, it'll be even smaller. For 5 children, smaller still, right? So that's just essentially how independent events work. Now, mutually exclusive events is basically if you have one event, you cannot have another, right? If you have a boy, you can't have had a girl, right? Because it's a boy. You know, maybe that's not such a great example right now, but if you have a straight flush, then you can't have 4 of a kind, right? I think. Probably getting a little bit out of my depth in terms of poker analogy right now. Right. So essentially, if you have one, you can't have the other, right? And so if you're looking at two possibilities, right? Let's say, I mean, rolling dice is kind of easier. Let's say you have a 6-sided dice and you need to get something to win, you need either a 1 or a 6. Let's say we're playing Dungeons and Dragons or something like that, you're casting a spell. Let's say you need a 1 or a 6 for that thing to work. Now, you can only get a 1 or a 6. You can't get a 1 and a 6, right? And so each one of those has a probability of a 6th, right? But because you can do with one or the other, you can have one event occur or the other one, and you still get your desired outcome. Then you add those together, because essentially you have 2 chances, right, at the same thing. And so then you add the probabilities together. So in that case, the probability of getting a 1 or a 6 is 1/6 plus a 6 is a third, right? And so the probability of getting one or the other is higher than getting either one separately. That's if they're mutually exclusive events. Okay, are you all with me so far? Okay, good. So one example that I like to use is let's say you know a couple and they have 2 boys and a girl. Right, so what is the probability? So what was the probability of them getting 2 boys and a girl? Okay, so now we have 3 events, but we now have different combinations of those events, right? So how many different ways can you have two boys and a girl, if you think about it in terms of order of births? I'll give you one, for example. It could be boy, boy, girl. What other ways can you have and still have two boys and a girl? So perhaps you can start with a girl. Yeah, there you go. That was a good guess, wasn't it, Joe? Girl, boy, boy. And what's the other one? Right, good job. So now you have three events, but you have three different ways that you can have those three events and still get the same outcome. So each one of these, what would the probability of getting a boy, boy, girl be? All right, so these are independent events, right? Boy 1, boy 2, girl 3. What's the probability of getting a boy, boy, girl? Not yet. No. Nope. So boy, boy, girl is half, right? Probability of getting a boy for your first one is a half times a half. Probability of getting a boy for your second one times a half. It's the probability of getting a girl for your your third child, right? And as generally put before, that's 1/8. Okay, what's the probability of getting a girl, boy, boy? Come on, love. Yeah, she's such a lazy dog. Correct, right? And the same for the third as well. So probability now, if a particular couple had a girl and then a boy and then a boy, could they also have had a boy and then a girl and then a boy for the same children? It's an easy answer. Begins with N and ends with O. So these are mutually exclusive birth orders, right? So if those three different birth orders are exclusive, what do we do with the probabilities? We add them together, right? Just a hair slow there, Sophia. So what is the overall probability of getting out of three children, two boys and a girl? It's going to be 1/8 plus 1/8, oops, not asterisk, equals, actually I've got to do this as 3/8 or 0.375. Yeah, exactly. Right. And so, oh, you're doing something a little funky there, JM. I think you're multiplying the lower number by 3. You just need to add them together. Ah, no worries. So you can also, and I've just got a minute left. You can see the same thing in a dihybrid cross, right? So what genotype you get, you can only have one genotype, right? So it can either be this or this or this, right? And you can only have for the other gene this genotype. So the probability of getting these, which are independent, is 1/16, right? Because you have a quarter probability of getting this genotype, you have a quarter probability of getting this genotype, right? Right, so that's 1/16, yeah? But for when you have, you can either have, let's see, here's another one. So you can either be homozygous wrinkly and homozygous for yellow, or you could be homozygous wrinkly and heterozygous for yellow, right? So the probability is that is 1/16 because it's quarter times a quarter. The probability of this, which is, exclusive, right? You can't be both, is a quarter times a half, right? Which is 1/8 essentially, or 2/16. But these different combinations are exclusive of each other, right? So you can either be this one or this one. And so the probability of being wrinkled in yellow is this plus this, right? Because they're exclusive, right? You can't be homozygous recessive and heterozygous for this gene and homozygous recessive and homozygous dominant, right? They're exclusive, right? So in that case, you add the probabilities of it being this or this to get the probability of having a wrinkled and yellow P, right, which is 3/16. And so genotypes are mutually exclusive, right? You can either be homozygous recessive, heterozygous, or homozygous dominant. You can't be heterozygous if you're homozygous dominant. You're either one or the other. But the different phenotypes, if things are going as you expect, these are independent, right? So these are independent events. So the probability of having this genotype or this phenotype essentially and this phenotype together, you times those two probabilities together, right? But because let's say this is round and yellow, right? You can't have this genotype combination and this one and this one and this one. You add those probabilities together, right? Because they are exclusive. So in many ways, a dihybrid cross kind of illustrates quite nicely, we're going over time here, the rule of mutually exclusive and independent. Okay, kind of gone a wee bit over there, so I'm going to call it a day right now. And we are going to be doing mitosis on Wednesday. So have a read up on that. Go through any of this stuff. If you have any questions, bring those with you to class on Wednesday, and we can go through them then. Whew. There you go. All done. See you on Wednesday, everybody. Oh, actually, hang on just a sec. I'll give you a, here you go. I'll give you something, a test to do just before we go. If you need to go head off, I'll post this in the chat. So here's one for you, Jelani, and anyone else that wants to do it. Oh, we don't have bold. Let's capitalize. So 2-gene test cross. Let's say So there you go. Generally, that'll give you something to think about between now and Wednesday, and anyone else that wants to have a go. So this is a test cross. It's not a dihybrid cross. It's a test cross. And your prediction is that the parent that you're testing, right, not the homozygous recessive testee, but the one that you're testing is heterozygous. How well do your data fit that expectation? There you go. And have bring some questions with you if you can't figure it out. Cool. All right, everybody. I'll see you Wednesday.